Hey kiddos, so up until this point we've talked about the types of reactions, we've talked about balancing reactions. Hopefully you've watched the states of matter, how to use the solubility rules video. Now we're going to talk about how to predict the products of double replacement reactions, okay? So let me go ahead and share the screen here. So one thing I want you to remember, when you're talking about the types of reactions, we talked about with the double replacement reactions, we have to make something. We have to make a solid, we have to make a gas, we have to make a water or a liquid of some sort in order for the double replacement reaction to happen. So if you make two aqueous solutions as your products, the double replacement reaction would not occur and you can simply put no reaction, okay? Now, when we predict our double replacement products, what we're going to do is we're going to switch the cations so that we can make two new ionic compounds. So what I say is that we're going to do the insides with insides and the outsides with outsides. So let me show you what that looks like. So here, when we do this, we are going to take our two inside ions, so the OH and the magnesium, we're going to put those two things together to form an ionic compound. We're going to take our two outside ions, the lithium and the nitrate, to make another ionic compound. And what you want to remember is you always need to drop and swap again. So you have to find those ion charges, drop and swap to make your new compound. So we want to remember that lithium is +1, hydroxide's -1, magnesium's +2, and nitrate is -1 when we're making those new compounds. So outsides with outsides, so lithium nitrate would be LiNO3, and then magnesium and hydroxide, you always want to put the cation first when you make your ionic compounds. So even though, like you see hydroxide first, you want to put that magnesium first because that's the positive ion. So it would be magnesium hydroxide is OH2. Now we want to check our state of matters for the lithium nitrate and the magnesium hydroxide, so we want to use those solubility charts, okay? So with lithium nitrate, we know that's going to be aqueous, 1, because lithium is an alkali metal and alkali metals are always aqueous. 2, nitrate is always aqueous also. Then we'll check for magnesium hydroxide, and that's actually going to be a solid. So this reaction would actually happen, okay? We're not actually going to balance this one here, but you would actually then have to balance your reaction. All right, so in this next one, we're going to do our outside ions together, remember? So the silver and the chlorine are going to go together. The nitrate and the calcium are going to go together. Remember, we want to drop and swap. So silver has a +1 charge, nitrate is -1, calcium is +2, and chlorine is -1. So the outsides together would be AgCl. And then the insides together would be calcium nitrate, or CaNO3 too. All right, so check your solubility chart to see what the state of matter is for each of these new products. AgCl, that's going to be a solid because chlorine, even though it's usually soluble, silver is one of those exceptions for it. And calcium nitrate is aqueous because nitrates are always aqueous, okay? So let's take a look at some more examples here. Maybe. There we go. All right, so again, when you do these examples, the outside ions go together, the inside ions go together. All right, calcium is +2, acetate's -1, sodium is +1, carbonate is -2. So outsides with outsides, insides with insides. So we have calcium carbonate, which is CaCO3, and we have sodium acetate, which looks like this. Now, calcium carbonate, when you check your solubility chart, carbonates are usually insoluble, and calcium is not an exception, so that's going to be solid. And this one, sodium acetate, would be aqueous because, like we've said, the alkali metals are always aqueous. Let's take a look at number 2. Outsides with outsides, insides with insides. Sodium is +1, chlorine's -1, silver's +1, nitrate is -1. So we have NaNO3, and it doesn't matter which product you write first, okay? If you put the outside ones first or if you put the inside ones first, it doesn't matter. What matters is that you're correctly forming your two new ionic compounds by dropping and swapping by writing your cations first. And the other one would be AgCl. All right, so NaNO3, that would be aqueous because alkali metals and nitrates are always aqueous. AgCl is solid because chlorides, although they are usually aqueous, silver is an exception to make it solid. Then here we've got our cations or our outside ions, and then our inside ions. Okay, so we have, now remember, so hydrogen here is going to be +1 because it's in the group 1. Nitrate is -1. Sodium is +1. Carbonate is -2. So we have H2CO3. And then we have NaNO3. Now, I know that this NaNO3 is going to be aqueous because alkali metals and nitrates are always aqueous. Now, H2CO3, when you see a hydrogen in front like this, that means it's an acid, and acids are usually aqueous, unless otherwise stated. So we're going to put aqueous with this one. Now, since there's two aqueous products, what I want you to do is write no reaction. No reaction. If there's no reaction, that means you wouldn't have to balance it. You wouldn't have to do anything else to this. You could just write no reaction and be done. So technically, if you wanted to check your states of matter first, you could do that. But it might be a good idea to write your products. Now, here's a little secret on this one. This actually does have a reaction because this is a special case of decomposition, but we're just not going to have to worry about all of that right now. So don't worry, just put no reaction. Then number 4, we're going to put our outsides together. We're going to put our insides together. Hydrogen, because it's in the group 1, it's +1, -1, +1, -1. Now, when you put this together, I'm going to put the KBr first. We know that's aqueous because alkali metals, always aqueous. Now here, please, please, please don't put HOH. All right, people always put HOH because you have a hydrogen ion and you have a hydroxide ion. Well, what's HOH? When you look at that, what has 2 hydrogens and an oxygen? Yeah, water. So that actually makes water, which we know is a liquid. And since it's making water, the reaction actually would occur. Okay, so that's how you do double replacement reactions. If you have any questions about how to do those, just let me know. I'll be happy to help. Bye.